Hi, this is Rucha Dhamdhere and I am here to present my EE275 Advanced Computer Architecture project, which is design of Altera NIOS to instruction subset architecture. NIOS 2 is a general purpose RISC processor core. It is a soft processor, means that the processor core is not fixed in silicon and can be targeted to any FPGA family. NIOS 2 processor is a hardware design that implements NIOS 2 instruction set. This is the hardware architecture of NIOS 2 processor. First stage being the instruction fetch stage, second being the decode stage, third being the execute stage, fourth being the memory access stage, and last being the write back stage. Let us see the details of each of these instructions in the next few slides. These are the 5 stages in the processor. In the instruction fetch stage, the instruction is fetched from the memory using address in program counter register and stores this instruction in the instruction register. This stage contains 2 important components, adder and multiplexer. Adder is used in updating the program counter at each cycle by adding PC by 4. And multiplexer is used in branch instruction, especially in branch where program counter needs to be updated. In the instruction decode stage, the instruction is decoded and next PC is calculated and also reads any operands required from register file. This stage contains 2 important components of register file stack and sign extend unit. The register file stack is 32-bit stack and sign extend unit is used to forward the immediate value in an instruction set. In memory access stage, it performs any memory access required by the current instruction. So for loads, it would load an operand from memory. For store, it would store an operand into the memory. And for all other instructions, it would do nothing. For instructions that have a result, the write back writes this result back to the register file. This includes nearly all instructions except no-ops and stores. In NIOS 2, there are 3 types of instruction set. First, I-type, second, R-type, third, J-type. In I-type, there are 5 fields for A and B that are used to specify general purpose registers. A 16-bit immediate provides immediate data which can be sign extended to provide a 32-bit operand. In R-type instruction set, there are 5-bit fields for A, B, C that are used to specify general purpose registers. An 11-bit OPX is used to extend the opcode. This is a J-type instruction set. In this, there is a 26-bit field that contains an unsigned immediate value. This format is used only in the call instruction. Now let's go to the simulation results for each instruction. Let us start with add I, that is add immediate. From the result, we can see each stage, the opcode in the first instruction, which is the instruction fetch, and PC incrementing at each stage. In decode, register A is separated out from register B, which is in hexadecimal. In third stage, the instruction execute stage, the result of addition of immediate value, which comes out to be 24 in decimal. Third stage is the memory access. This instruction being add does not actually have to do anything with data memory. In the write back stage, the data that has to be written back to the destination register, and we can finally say that the result is written onto the correct address. Next instruction is add R, that is register to register adding, which is similar to the register to immediate. Here we again see in decode stage, contents of A and B are separated and result of addition is clearly being displayed in execute stage. Memory access again is of no use. We are not using the data memory. The write back stage contains the data that needs to be written to the register and exact location of the register, and finally the contents are written back. Next instruction is ORHI, which performs OR function with the higher index of immediate value. So in decode stage, contents of register B pulled out, and we can see in the execute stage OR being done with the high indexed value and result being passed on to the next cycle, and then from memory cycle to the write back stage. So the write back will have the contents to be written back to the location. So in the last stage we can see the result being written to the desired location. ORHI and ORI are similar, only that ORing happens on the lower bits of the immediate value. So in this instruction, we can see that the flow of the instruction is as the ORHI, and we see that the result 20 is being written to the desired location in the final cycle. Next, in the mul instruction, which is an R-type instruction. Here the instruction provides us with 3 registers. So we need to multiply the contents of 2 registers and store value to the third register. So in decode stage, values are selected, removed out. Execute stage executes multiplication function. Again, memory access is not used as we are not dealing anything with the data memory. The result is written back to the desired location. BR is J-type instruction, which is a branch instruction without any condition. So in this case, it is just jumping to same program counter again and again. So we can clearly see that from waveform and pointers indicated. These are the results for BLT, which is branch if less than, which is similar to branch instruction, which is J-type instruction. Just that the branches only when condition is satisfied. In this case, it checks if contents in R0 register were less than that in R4 register, and if it is true, it would branch to the desired program counter. In the load instruction, it uses the memory access stage because it has to extract the data from the data register and put it into the register file. Therefore, the contents from register file are extracted and are given to write back for putting it to the desired location, which can be seen in the last cycle. Store instruction uses memory access stage. Here the data from register file is being transferred into the register memory. As we can see, the final output is stored into the desired location in data memory at 100th location of data memory. So this is how we got the desired results. Hazards that are encountered during design are of 2 types: data hazard and control hazard. Stalling was used to eliminate this problem. Thus we say NIOS 2 architecture was designed using synopsis simulator. Results were verified and tested. Hazards were handled using stalls. Design is flexible enough for developing above features and modifications explained in future work, which is branch prediction, Booth's algorithm, which is applied for multiplication and data forwarding. For more number of instructions inculcated into the system to extend the functionality of the processor. Thank you.